Okay, so now in section 2, we're going to start looking at a trend line to help describe what's happening with our scatter plot. And that trend line, when not really done mathematically, is really called a trend line. But what we're going to do is a least squares regression line. And that's really important. And a lot of times we'll call it a regression line, just to be, just to shorten it up. But one of the main things that they really want you to be able to do, especially when it comes to multiple choice questions, is interpret what is the purpose of a least squares regression line. And so this is our actual definition. What does it do? And the least squares regression line minimizes the sum of the squared residuals. So let's talk about what is a residual. So what happens is we get this line occurring that is kind of trying to sum up what's happening with that scatter plot. And we do this all the time in real life. We'll take a bunch of data and we'll use that to kind of analyze, and we use it to help predict stuff. So what's the probability, or what's the likelihood, or how many accidents will this person get in, and all that sort of stuff based on data. And so if that's my prediction line, what I actually have then is these are my actual data points. Here's a data point, data point. So all of these are data points. And notice the data points aren't on the line. And so then we end up with this idea of a difference. So right here, I have a difference between these two. And in fact, this difference is saying that my line is going to predict this value, but my actual value is here. So it's under predicting what's going to happen at that point. And so this is what we would call, it's a positive residual because it's above the line, but it is under predicting what is happening. Now we want our line to predict as accurately as possible. There's no way we're going to be able to draw a line that's going to go through all the points, but we want those values, these residuals, to be as small as possible. Now the problem is that when I add up all these residuals, they're always going to add up to be 0. Residuals always add up to be 0. And so I can't just look at, well, if I add these up, then I'm going to figure out what's the best. Because we'll have positive ones balancing out with these negative ones, so on and so forth, and they all balance because that's kind of the purpose of that regression line. Well, the best line to represent our data won't just take this into consideration, it will actually take into consideration the square. So that value squared. And why squaring? Because squaring gets rid of the negative numbers. So now when I add it up, it may make the number much bigger, but now we have positive numbers, and now it's something we can work with. So we're trying to make, when I square each residual, which that's the reason why we call something to the second power squared, is because this times this gives me squared. So we can visually look at it as a square there, and we're wanting these areas to be as small as possible, or those values that when I square it each time and I add them all up, we want them to be as small as possible, because if we have the negative and the positive, they always balance out if it's a good trend line. But for a regression line, we're looking at these smallest values for all of these squares. So our purpose is always getting these squares as small as humanly possible. And no matter how we tilt the line, we're going to have little squares, but we want the smallest squares. So we may end up with some big ones, but as long as overall they add up to be the smallest possible, we're fine. Because the bigger or the smaller our correlation, or the closer to 0, we're going to end up with those big residuals. And so we're going to end up with big R or small r values because there's so much scatter. And so it's not going to be a very good regression line. So the tighter fit to a line, the better our regression line is, the better prediction value it is. So how do we do a regression line on the calculator? Okay. So the very first thing you need to do is, if you're going to do a regression line, you want it to calculate your correlation for you. So we're going to go ahead and look at our calculator. And the first thing we're going to do is turn it on. And then if we, let me zoom out a little bit so we can see the calculator better. Down here somewhere is catalog. There we go. So down here on the 0, you can barely see my finger. Woo, there's my finger. I come down to 0, and above 0 says catalog. So if I go second, catalog, and I can go down, if I hit the letter D, let's see, D is this one right here. I want to look for diagnostic on. A diagnostic on allows us to see that R value and also shows us R squared. We want R squared. So we're going to look at diagnostic on, and that's going to allow us that when we do the least squares regression to go ahead and get that correlation value. It'll just automatically do it for us. So let me go back to here. So these are all of our different directions for doing this. But I'm going to go ahead and go to the problem, and we're going to show you how to do it with the problem on the calculator. So the first thing we need to talk about is interpreting a regression line. Very, very big, very important. In fact, a lot of multiple choice questions will say, what's the correct interpretation for the slope? What's the correct interpretation for y-intercept? So our regression line looks like this. It's y with this little hat on it, and it's actually called y hat because it's our predicted y value, not our actual y value. So y is saved for the actual y value, and y hat is a predicted y value. And so we want to make sure that every time we're working with our formulas, our regression formulas, we're using y hat. So we know that it's the difference between our predicted versus our actual value. And the actual value comes from the scatter plots. Then we have B0. This is kind of like my beginning value at 0, also known as our y-intercept. Now, how we interpret the y-intercept. It is our response value, also known as our x value, or y value. Oops. Y value. When your explanatory value is 0. So depending on what those categories are, what am I using to predict what? So last time I was saying my response value is backpack weight, and my explanatory variable was the human weight. So what was the backpack weight when the human weight was 0? Doesn't really always make sense based on the context, but you have to be able to verbalize what it's supposed to mean in theory. Okay, our slope is this B1 right here, which makes sense because slope is a rate of change, and we always multiply that by our x value. So B1 is our slope. And so this kind of looks like a y equals mx plus b, just kind of flipped around, like y equals b plus mx. Because typically when you're going to graph a line, you always start with that b value, so it makes sense to have it first. I graph this, and then I use this to help move up or down based on whatever my slope is. And so that's how we, in stats, work with those equations of lines. Now our slope is, remember slope formula was y2 minus y1 over x2 minus x1. So when we're looking at it, we're looking at how do the y's change over how do the x's change. And triangle just means change. So what's the difference in the y's? Like how do they change? What's the difference in the x's? How do they change? And we actually use that to help us interpret. And so our y's are really our response variable. So how does my y value change for every increase of 1 in our x value? So as I keep adding a number to x, we're going to change by this much in my y. So if my slope is 2.58 and I was working with the backpacks, then my backpack weight changes by 2.58 pounds for each increase of 1 in human weight. And so that's where you have to be able to identify that explanatory variable and that response variable. So when we do these interpretations, you know what goes where. Okay, so now we're going to move into our sample problem with used Hondas. The following data shows the number of miles driven and an advertised price for 11 used Honda CR-Vs from 2002 to 2006 model years. Use the calculator to find the equation of the regression line. So we have to think about what's our explanatory variable and what's our response variable. It makes sense for miles to explain our cost, because the more miles probably on it, the vehicle, the more miles it has on it, the cheaper it's going to be. Because as you get higher in miles, the more maintenance you have, and the closer you come to having to replace your engine and tranny and stuff like that. So let's look at our calculator. I'm going to turn on my calculator, and I'm going to go to my stat, and I'm going to go edit, and I'm going to put in my list. Now, my list is already in here. This is all of my X values. So this is the thousands of miles that are on the car. And then over here, this is the cost for each car. And so once I have that in there and I know, okay, this is my X, this is my Y, now I can actually calculate that regression equation. So I'm going to go ahead and go to Stat. I'm going to go over to Calculate. And there's a linear regression AX plus B. That's not what we want. We want our form in Stats form, so I'm going to keep going down. And there's linear regression A plus BX. There's our format with our y-intercept, our slope, and then X. Okay, my X list is an L1. My Y list is an L2. And now if you want to graph the line or do any calculations with the line, you're going to want to store your regression equation. Now, if you have a TI-84 that has been updated, you can hit alpha trace, and this will allow you to store that in that Y equals. And you can choose which Y equals to put it in. I'm going to put it in Y1. And it will program that in there for you. Now, if you have a TI-83, you have to instead go to vars, yvars, function, Y1. So this is why I really like the TI-84. There's a lot more shortcuts for it, but either way, there's a way to get there. And then we can calculate. And so this actually gives me my value. This is my y-intercept. So when there's 0 miles on the car, our car would cost $18,773.28. The price goes down $86 for every mile, every 1,000 miles increased. And then here's my R value. This is my correlation, a negative 0.87. So how would I actually graph the scatter plot? So in my scatter plot, I can go, or in my stat plot, I go second, stat plot. I go into the first one, I turn it on, and the very first graph is a scatter plot. Here's my X, my L1s, my Y's, my L2s, and I can graph. Now I don't see any of my information, of course, because my numbers for Y are really high. So let's zoom 9. And now we see the scatter plot with that least squares regression line. And so we get a really good idea of what this is supposed to look like. So if I ever ask you to sketch this, you can actually sketch this. And you can actually trace around and get the coordinates of the different points. Okay? Okay, so now we're back to our slide. What is the correlation? We found our R to be negative 0.87. What is the equation in context? Y hat equals 18,773.28 minus 86.18x. And then in context, what is Y hat? Y hat is the predicted price. and X is our miles driven. And that's in thousands. So interpret the slope in context. So my slope is negative 86.18. So what's going to happen is our response variable cost changes by negative $86.18 for every increase in X. And our X is 1,000 miles. So every time I add 1,000 miles onto that car, that price is going down $86 every single time. Okay, interpret the y-intercept in context. So y-intercept is when I have no x, the y value when the x is 0. So when the car has 0 miles, it will cost $18,773.28. And again, as long as you're saying the same thing, that's really all that matters. Okay, predicting from a regression line. The purpose of having that regression equation is to be able to predict what would happen. And so please remember that y is the actual value, so the value from the scatter plot or the dots, where y hat is the predicted value. So it's the value on the regression line. And the difference between the two, and we do this actual minus predicted, also known as kind of AP, that's how I remember it, AP, actual minus predicted, is called the residual. And that's that vertical deviation between what actually happened versus what we're predicting to have happened. So in our previous problem, we're going to predict the price of a car with 49,000 miles. Now, there are two ways you can do this. You could actually plug 49,000 miles into the equation and kind of calculate by hand, or you can go to your calculator. So I'm going to show you on your calculator. So if this is my calculator, and remember how I programmed that formula into y1? My calculator is so fabulous that when I exit out, I can do y1, so again that alpha trace, and I can say, hey, in my y1, I want you to plug in a certain value. So what was that value I wanted? 49,000 miles. So I want to know, what's the value at 49? Why'd I use 49? Because all my data is written in thousands of miles. So 49,000 miles is how I would put that in. So I'm plugging in 49, and it actually tells me my answer. It plugs it in and calculates it for me. So nice to have that calculator there. Or you could, again, you could go ahead and go back to that regression equation and do the 18,000, what was that? 773, and then minus the 86.18 times 49. But be really careful about that, because they're going to tell you in context, and you have to remember that your data is written as 49. And so you could actually calculate this by hand. Let's see, the answer I got from the calculator, calculating it was 14 550.36. And if I do negative 86.18 times 49, and then I add the 18,773.28. So when I calculate it this way, I get 14,550.46, off by like 10 cents. And why is that? Because this used a rounded value, the calculator used the full decimal. And so it gave you a more accurate answer. So if you had a choice, this would be the answer that you would go with. Okay, extrapolation. Big, big, very, very important idea. I don't know how many stars I can write around this. Very, very important. So extrapolation occurs when you use the regression line to predict out for a value outside of your data's domain. So when you're looking at our original table, our domain is our x values. So when I'm looking at this, if I predict any lower than 22,000 miles or any higher than 86,000 miles, I'm doing what we call extrapolation. I'm going outside our scope of data. And so we don't know what really happens, because when I graph this, it looks linear. But outside of that, if I throw in data points from outside of there, I might find curved data. And it would actually change how everything's predicted. So we must stay inside of that domain, or the x values for our data. So we never go lower or higher than the x values we know, because again, we don't know what's going to happen. We don't want to take that huge risk. So when we look at the previous problem, can we predict a car with 250,000 miles? And let's look at that table. The highest we went was 86,000 miles. So we don't know what happens. All of a sudden the cost could drop, or they could level off. And in fact, a lot of four-wheel drive vehicles will level off at a certain price just because they're four-wheel drive vehicles. And so we can't do that because it is extrapolation. We just don't know the behavior of the data beyond 86,000 miles. Okay, so that's it for the beginning of 3-2. Remember, we're going to keep doing this over and over, so if it seems like a lot, that's okay. The video's here to re-show you over and over how to do this. And then your textbook also has directions on how to do the regression line and the scatter plots.